Well, thanks again for the invitation. My name is Jose Liste. I am a technical marketing engineer at Cisco. And in the continuation of our demonstration at the tech field, I'm going to show the second demo, which is moving us from segment routing MPLS. Remember, Clarence was talking about the actual execution of segment routing in the first 2 years was focused on MPLS data plane for multiple reasons. But we are executing on IPv6, and these are the proof points. In particular, we're going to show you a prototype of the multicast, or what he calls the spray multicast use case. So 2 simple objectives. We're going to show you the spray multicast use case, and we're going to show it to you in an end-to-end portfolio. We're going to be using segment routing v6 capable devices, which are software-based, open source, running FDIO BPP, or hardware-based segment routing v6 platforms, which are in both operating systems, ASR 9K with XR or ASR 1K with iOS XE. Okay. Now, as we all know here, segment routing is all about packing instructions into the packet. So we make the analogy that the instructions are included into the packet. And for SRv6, for those of you out there in the virtual community who are not familiar with it, we're now packing instructions into a routing header for IPv6. This is a routing header type 4 that was defined, and it's called the segment routing header, or SRH. So if I have a traffic that wants to go from A to H, I can include an SRH header that says, let's make a stop on C, then continuing on to F, and then going on to H. So the IPv6 addresses are my instructions. Of course, we need to remember, so why are we doing all of this? So it was reiterated multiple times. We're bringing control back to the application space. We are going to be using ECMP more broadly, so better use of my links and my infrastructure. My network will be simpler. I'm not going to be running more protocols that I don't have to run, and the operations will be simplified. I hope you can follow the picture. I think I'm going to try to explain the use case in more detail than John and Clarence did. I have a network that is running just purely IPv6 unicast. And that network is also my SRv6 domain. On that network, I'm going to have access routers, which are SRv6 capable. I have transit routers that may or may not be SRv6 capable, but if they're in the instruction path, they are. I made an omission of not showing the transit router there. And I also have an insertion point. I have a compute node that is going to be also SRv6 capable. At the bottom, I have an IPv6 multicast network where my subscribers are located. If you follow, every access router will have an IPv6 address for its loopback, let's say X::1, :2, :3. And I have an IPv6 multicast source, Y::1, which is multicasting on one particular group, FF18::1. The use case calls for the ingress replication of the multicast feed coming from the video source into multiple copies that get to the access routers via unicast. John was making a statement. These access routers are pretty stable in the network. Via some learning, the compute node can discover what are all of the access routers that want to get a copy of the traffic. So if you look at the headers, let's look at this bigger one that I expanded. I'm going to be sending a packet to X::1 coming from the compute. Source is Y::1. And my SRH header, it includes the multicast group in it. So the packet is moving between the compute and the access router via unicast. And I'm not doing anything fancy as far as going detours in the blue cloud, which I could. I'm just saying, go via IGP to 1, or to 2, or to 3. And the next instruction in the SRH header will include the multicast address, FF18. So you can see how the other 2 copies are going to 2 different places, and the SRH reflects the multicast group in it and the destination of the proper access router that I'm going to. What is going to happen, once the access router receives this traffic, he will actually clean the SRH header, he will promote the next segment to the destination address, and now I have a multicast packet that gets replicated to the household. And that is the use case. I leverage IPv6, SRv6 for unicast transport. I replicate my multicast in any place I want to for a particular application via the compute elements, and I do multicasting from my access routers down to the households. So I no longer need to be running IPv6 multicast on the Blue Cloud. So we have a test bed. This is a test bed just across the street. We're using the 3 key components. We're using a BPP device acting as the ingress replicator, as an MPLS forwarder, SRv6 forwarder. I have an ASR9K as a transit node, and I have an ASR1K as a terminating node. So in the first step of the workflow, which you will see, I have a traffic generator that will issue joins, MLD joins for the group FF18. So now I'm going to build MFIP state on the ASR1K to replicate onto 2 local interfaces for group FF18. Okay? So that's my household joining a channel, my set-top box. Next, my traffic generator will actually simulate the source, so it will be sending traffic into the multicast group FF18. So this is my multicast packet coming onto my compute node, the BPP node. My BPP node will be configured with a multicast replication policy, segment routing multicast replication policy. And now he's going to build, in this very restricted topology, I want to show you the replication. So I'm going to actually create 2 copies that are going to land in the same box. That is not how I would do it in the production, but here I just want to show you that we do the replication. And you see here, every copy, every replication has a different segment list. The first copy says, go to Cafe 2 on interface 12A, which is going to land me right here on this top interface. And then the next instruction says, go on to Cafe 3, that's the SR1K. And then the next instruction, we are multicasting. The second replica says, go to the Cafe 2, but this time go to 12B2. That's the IP address on this link. So literally, I'm creating 2 copies that will end up here in the 9K2. Of course, I don't need that second copy. I'm doing the second copy for the purpose of the demo, so I'm going to throw it away. I want to work with you on the top copy. So what happens with the top copy? So the top copy arrives in the SR9K2. He's now SRv6 capable. What he's going to do is he's going to see himself in the destination address of the packet. Okay, so he says, oh, this is for me. And then what he will do is he will actually decrement the segment left field in the SRH header, and then he will promote the next segment as the destination address of the packet. You see here how Cafe 3, which is the next segment in the SRH header, becomes the destination address in the outgoing packet. So the packet going out now has DA of Cafe 3, and the segment left is decremented by 1. Okay? What would have happened if the 9K2 was not SR capable? Well, then I don't put him in the segment list. It's just doing IPv6 forwarding. Okay? Now, Cafe 3 is receiving a packet with himself as the DA. There is a bit also in the SRH header that's called the clean bit. So what he's going to do is going to say, okay, this is for me. He's going to process it, and he's going to remove the SRH header. Now he will promote the last segment, segment 0, which is FF18, the multicast, onto the DA. So now he's going to look up and see who wants this multicast group to be replicated. And from the very first step, I know that these 2 houses on these 2 ports want to see that channel. So I'm going to replicate 2 copies onto those 2 interfaces. This is just pure multicast-based replication on the 1K.
Is there an implicit clean when you reach the end of the...
The clean is actually configured as a source. So when I show you the BPP, I want to build a policy with these segments, and please clean it out. So it's not implicit, it's explicitly mentioned in the header at the source. So the source said, I must not let the SRH continue. I must clean it. So it is explicitly configured at the head end. I believe John Lady in the morning showed a case where he didn't want to clean it up. He wanted to continue onto the equipment at the home. All right, so now we're going to take you then to the devices. Get my cheat sheet here. So the topology is much simpler, so I still have a picture in case that you want to refresh your memory. I have this BPP 9K ASR1K traffic generator. Okay. I'm going to come back first to the 1K, which is my multicast replication point. What's happening? Okay, I want to repeat that. Okay, if I look at my MFIP state, I'm looking for state for that group, multicast group FF18. I don't have any replica. I don't have any customer who wants to get that group. So it's empty. I'm going to go to my traffic generator, which is Ixia, and I'm going to start my protocol emulation. So I'm going to simulate these subscribers at home. So here you will see my MLD hosts. All right, so they're green, so I assume that they already sent the join. When I come back to the ASR1K, and I run this alias, I now have state. So I receive 2 joins for that group FF18, even for that source called CAFE4. So I have 2 local interfaces where I'm supposed to replicate traffic from that IPv6 multicast. First step. Now we're going to go to the forwarder BPP. So I'm at the BPP console here. So for those of you who are not familiar with BPP, we have open source BPP, and you can get to the FDIO website and download it. And I was told that even this functionality for SRv6 and ingress replication is also open source since April already. So here you can see how I have show SR policy. I have a multicast policy called MCAS1. And that MCAS1 policy has multiple SR tunnels in it. I have SR tunnel SR1. I have SR tunnel SR2 in the same multicast policy. These are my replication copies, my replicas that I'm going to be building at BPP. Okay. If you look, I think the most important thing to take a look now is the segments of those policies. The first policy, if you remember, says go to CAFE2, the top interface 12A, go to CAFE3, that's the SR1K, and put the multicast address at the bottom of the instruction set, FF18. If you look at the second policy, I have exactly the same with the difference of the first segment, which says go to the bottom link 12B. Your question about the clean, I think the cleanup is here. I have a cleanup true, so is actually asked for. So the cleanup bit is set, the flag is set. So when I get to the very end of the SRH, that device will clean up the SRH. It's clear count.
Okay, so it's implicit that when you reach the end of the segment list,
it will be cleaned.
It will be cleaned.
No, yeah, when you say implicit, I got confused in the way that you explicitly requested the cleanup via the flag.
Right, so you can either clean or not clean,
Yes.
but it always happens at the end of the path.
Yes.
Okay. And the segments in the policy here are built manually, or is there an algorithm that runs that defines what these segments are?
Right here, they're actually just manually added.
Okay.
Yeah. you could envision that if somebody has an algorithm that once I learn the topology and the endpoints, I can just configure BPP to do it, yeah. I can pass it on.
So there is an API to BPP to do this?
I'm not an expert on BPP. I actually believe that BPP has actually multiple ways to get in, whether it is with conf-d or whether it is netconf or,
Okay.
yeah. Right. So we're going to look at the interfaces. Right now, actually, I'm sending no traffic. So if I look at my ports, 203, that's the port that connects me to the traffic generator, and my downstream ports, there is no traffic there. Okay? So now I'm going to go to my traffic generator, and I'm going to start my traffic. I'm going to be sending just a sample, I'm going to be sending 20 megabits per second from my simulated source, and I'm asking BPP to replicate it twice, 2 copies. And if we look at the speedometer here, we can see how 20 became 40. So already my end-to-end is working, though we're going to walk it through. So I'm injecting 20 here on the left, and I'm already getting 40 from the right-hand side. Okay. All right. So let's go to BPP again, and now we should see some of the traffic counters on BPP. Show interfaces. So now you can see how packet is coming in by Gigi 203, packet count, let's say 205,000. And I have transmit packets of that same number, 205,000, on 2 interfaces, 500 and 501. So this is BPP now replicating that multicast packet twice. And the packet is being replicated with the SRH header and IPv6 unicast on the IPv6 header section. Okay. So we move on to the 9K. So the 9K is in the middle. So we're going to clear counters there. So we have fresh counters. Okay. So here's my incoming traffic from BPP, 28,000 packets after I clear. And here I am, I'm so sorry, no. I'm receiving 2 copies from BPP onto 2 interfaces, remember? So I'm here. I'm receiving 2 copies on the 9K in these 2 links, and I'm replicating, I'm sending it once via this 3rd link. So 2 copies coming in. Remember, I'm dropping one of them because I'm only using for the purpose of this demo to show you the replication. And here's my outgoing copy that goes to the ASR1K. Okay. Now, here I'm doing SRv6 SRH header processing. So I'm looking at the SRH. The packet is destined to me, the SR9K. I'm moving the segment left pointer one place in the header, and then I'm promoting the next segment onto the DA. And I'm going to prove that to you when we do traces on the ASR1K, which we're going to go next. So let's clear some counters in the ASR1K. I'm now sitting at the end of the segments of the path. Let's look at some accounting. Yeah, this is good. I'm actually getting 38,000 packets coming from the ASR9K. And these are all IPv6 packets. And the packets are getting replicated according to the MLD join, the MFIB state. So they're going down via interface 123 and interface 124. This is the multicast replication that is happening on the ASR1K, down to the home. If we look at the MFIB state, we can see that there has been actually a lot of packets that I have already forwarded there. There are 850,000 packets which were hardware forward for this multicast group down to these 2 interfaces, 123 and 124. I know that because I'm getting traffic on the Ixia, so that is happening as well. I think back to our, can you show me these SRH headers? Because until you don't see it on a sniffer, I guess it's all, you have to believe me, right? So let's not do that. You don't know me. So we're going to do some debugging. I was asking the developers, do we already have the Wireshark extensions for the route header 4 to decode this? And I was told no, but yesterday I was told, oh, maybe yes. So somebody was working on it. So, but for now, we're going to look at hex, okay?
Sweet.
Yeah.
That's what we need right now.
Yeah, hex is good. So I'm going to start a packet capture on the ASR1K. I'm going to let it run for a few seconds. I'm going to stop it.
So in the configuration of the 9K, is the dropping of the duplicate stream something you manually configured, or is that automatic? Okay,
So I have an access list.
okay,
I have an IPv6 access list. It says drop all IPv6.
okay.
Yeah. Manually configured. Okay, so I capture packets. Now let's look at the packets. So dbg show 0.
Because 3 doesn't necessarily know, I
No.
guess, that the 2 links that it has go to the same place.
No, 3 only has one link. So 3 only has.
I'm sorry, VPP.
Oh, yeah, BPP doesn't know.
Yes.
No, BPP doesn't know. No. But because I had a limited topology on where to show you this, I wanted to prove that I'm doing the replication. So I'm doing the replication to the same box. Okay, so this is one packet on that trace. So let's have a look at that packet. This is one packet that came via the interface connecting to ASR9K. So again, I am in the ASR1K doing captures. I'm here. I receive a packet from the ASR9K link, this 10 gig. And I'm sending it out on this interface facing the home. How do I know that this is already a multicast packet going to the home? I know that because look at the source and destination IP addresses on that packet. It is the IP address of the source, CAFE4. This is my traffic generator. And FF18. This is a multicast packet. So this packet is actually going down the wire towards the homes. This packet has no SRH header. It has been cleaned up. I think the most interesting one is the next one that I'm going to show you, which is the packet that came from the ASR9K. So this is coming in from the ASR9K. Look at the source and destination IP addresses. Source is CAFE4. Destination is CAFE3. So let's actually come back to the destination address of the packet coming in with the SRH is CAFE3. Here's the next segment. And the source happens to be the source IP of the traffic generator. And if we go deeper, I have my color coding here, we can see the SRH. Where does it start?
FA3 on that line.
Yeah, right here. It's all of this. It's all of this. So when we encode the SRH header, the segments are put in the opposite order. So the very first segment is the last. So it's the FF18. The next segment is CAFE3. And the next segment is the copy that went via the top, CAFE2 12A. So here's your SRH with 3 instructions as they're being received by the ASR1K and before they get stripped out. So this is your frame with the SRH header. So what this guy did is he processed this packet, he removed the SRH, he promoted FF18 to the DA of the packet, and then multicast replicated down to the home.
And where does the strip bit live?
Oh, well, so now
Sorry, I know you weren't prepared for that. But
it's here.
okay.
It's here somewhere.
So it's not part of the SRH then?
Oh, no, it is in the SRH.
It is? Okay.
It is in the SRH.
All right.
So if we go, yeah, so.
That's what I was thinking it would be.
No, it is. So if we look, I think I have a presentation that might show you this.
That's right. You don't need to prove to me with a...
Oh, no, it's okay. It's okay.
Sure.
I have it right here.
You don't know him.
Exactly.
Yeah, I don't know.
You don't know me. You don't know where I live. Yeah. All right. So, no, but this is perfectly fine. here you see this is the SRH, so this is a route header type 4. It's here in the flags.
Okay.
So it's a 16-bit flag. It's bit 0 is a cleanup flag. So it's right here. Yeah. By the way, this is a public presentation for SRB6 if somebody wants it. Okay, so now the very last piece, we're just going to stop the traffic at the traffic generator. So we're going to stop all the traffic. We're going to go to the counters. And here we see all the traffic that was sent by the traffic generator as multicast, so 2 million packets, 230,027. And here are the replicas that came back on the other direction. And these two numbers match the transmission. And this is the demonstration for the multicast spray use case of SRB6. When I unicast my multicast in my core, no multicast IPv6, and then I multicast from my access node down. Any comments, questions? It worked. And this is a shared topology.
So we don't know.
This is a shared topology in Ottawa, and somebody was connecting to the routers an hour ago, and so. Oh, really? Bertrand, you're here. What? I'm sorry. So the question was, in what release are you going to be shipping what you just saw? Yeah.
I mean, we will try to get that in 621, 631, depending. They release in the detail, like always, but there will be some part in 621 and some part in 631. That's what we are targeting. That's what we are shooting for.